morning. Good morning, everyone. I'd like to deliver it in Mandarin because it has a lot of terminology in it. Maybe it's challenging for the simultaneous interpreters. I will try to be slow and I will explain. I'm very happy to have this opportunity to deliver this presentation and discussion because many focus on the high-rise buildings, like the design, energy saving, and economy for those high-rise buildings. But today, I will more focus on the building cluster and also the comfort for the pedestrians. So my topic is CFD simulation of urban pedestrian winter comfort optimization in high-rise building cluster. From the perspective of the series, I conducted my research. First, I'd like to talk about the research background. And secondly, the basic series, and I will share with you a case study and then the results and recommendation. First, the research background. As we look at the four charts, I'm sure that you're quite familiar with it. First, the Shanghai Lujiazui, and they have some similarities, very high, very down in terms of the building clusters. So it will bring some positive and negative effects because it's quite dense, quite high. So we can see that this kind of cluster will bring some impacts on our environment. First, let's look at the positive impacts of those building clusters. First, it can improve comfort, and with good ventilation, it will bring comfort to the people, so that and it can also improve the indoor natural ventilation and reduce the energy consumption, because with the natural ventilation, we try to reduce the artificial ventilation. And thirdly, we can try to reduce the concentration of the pollution, so that we can quickly disperse pollution and we can try to improve the air quality. As for the negative impacts, it will affect the existing buildings. For example, for a high-rise building, it might bring some negative impacts on the neighboring buildings, like the ventilation and the other aspects. And for the building clusters themselves, they all have some problems. So would it quite in coordination or in harmony with the other buildings? And in line with the literature, sometimes it will also affect the flow of the neighboring shops. Sometimes it will reduce in the decrease in the visitor flow, and sometimes we also had those casualties because of those high velocity. So we hope that we can do some research. I cited them from the internet. First, we have two methodologies. First, numerical simulation, and then the wind tunnel. And a couple of days ago, I also attended a workshop on the wind tunnel, because this is the research based on the structure. If we use this wind tunnel method, it is quite expensive. But for the numerical simulation, it also has some problem, like the reliability of the results. So it is kind of a contradiction. Let's look at this slide. In recent years, ever since the numerical simulation, starting from the 1979, at that time, computers were not quite mature. They have the calculation based on the mesh or the grids. They were doing research based on one single building. So with the urban sprawl and the urban planning and the requirements for the comfort, and then we have the large-sized or middle-sized simulation. This is the development. And secondly, I will talk about the basic theory. It's kind of a lengthy part, because in our research, we found out that for those larger-sized simulations, we also encountered some problems. That's why I want to go into the details first, because for the simulation, we have two guidelines. First, in Japan, they proposed this guideline, and one in Europe, cost C14, and the other from Japan, AIJ. They have some similarities and also some differences. For the Japanese perspective, it is somewhat different. In terms of the inlet, they are based on the height of the buildings, and for the outlet, Japan proposed 10 times, and for Europe, 15 times, so that they can try to avoid those impacts from the outlet. As for the inlet boundary requirements, the Japanese side proposed this equation. And for the European, they have the other equation. As for the turbulence model, they're also different for Japanese perspective and also for cost C14. As for the grid, they're quite similar. So minimum of 10 grids on one side of the building, so that we want to have a more accurate calculation, and it is we cannot just based on that. We also try to look at the physical reliability, velocity, and the temperature, and etc. That for the convergence results. First, what will be the mindset for our research? As I said, wind tunnel testing is quite a reliable method. However, it's quite expensive, and it is quite time-consuming. If we can use numerical simulation, what will be the problems? Is it still reliable and accurate? So based on that, so how we can do the simulation, and how we can distribute the grids, how we can select the model, and how we can validate the accuracy of the grid, and also the impact of the boundary, and the inlet, and also the judgment for the convergence, and etc. So based on the aforementioned methodologies, this is based on the European methodology. We will try to follow the requirements, but maybe we are not blindly copying that model. We have to take into account of the accuracy of the computer. We will make some slight adjustment. And secondly, the grid solution. So grid is very important for the accuracy. After the modeling, we'll have those initial mesh, and then we'll try to refine the mesh at 1.5 height, at least 3 to 4 grids. And we will try to maintain 10 grids in the final mesh. And we hope that we'll try to increase the thickness. So we will have 3 calculations to validate the accuracy of the grid. This is the turbulence models. As we all know, for the turbulence models, they have the RNG standard equations and etc. So in China and also elsewhere, and they hope that they would do the large eddy simulation, but for our regional simulation, it's not quite realistic, because it's quite time-consuming, and the bearing capacity of the ordinary computers is not that desirable. So we finally choose the NG-KE2 equations. We want to try to explain in the following content. In Japan, they conducted an experiment. We cited the results to validate the accuracy of the models. From the left to right, this air flows, and they have those kind of points for the monitoring and the calculation. We used a standard KE equation, the first order upwind scheme. In the inlet and also the downstream, those kind of deviation reached 40 or even 60%. Secondly, we have the RNG KE equation and also the first order upwind scheme. Even if it is better, but still, after the downstream, and the deviation is still a little bigger. And for the black, those are the results from the experiment. And if we use second order upwind scheme, we think that the results are better, but still there's some deviation. If we use a reliable KE equation and the second order upwind scheme, after comparing the inlet and the downstream, and they can try to meet the engineering requirements. So that's why we selected that model for our simulation. And secondly, the atmospheric boundary layer. So this is 500 meters high. This is a 2D model. We want to try to validate the changes of the velocity and how it will affect the inlet. So in fact, if the velocity is like this, people might think that the final result is as this, but actually it's not. And we can validate this model. If we look at this chart, horizontally it's velocity magnitude, and vertically it's position. If the x equals 0 and etc., they'll have the corresponding velocity. We think that the velocity is changing, and this is the height of 100 meters, and we'll do the validation. We think that those kind of deformation is quite big, and also 10 meters. Deformation is quite apparent. Why they have this severe deformation? The inlet wind velocity has deformed till the downstream. So we're paying attention to the 1.5 meters high. So it has a great deformation at 10 meters high. Then it will greatly affect our results. How can we solve that? And then I will go into the details. And now let's talk about the wall functions, the FX and the fluent and etc. They also have those figures or values. Sometimes it will reach 10 meters, 20 meters. If we use a wall function, it might have this kind of contradiction. As for the Japanese and the European standards, they have 3 to 4 grids at the height of 1.5 meter. So this is a contradiction, and this is a challenge actually for us. So in all the commercial softwares, they also have such kind of problem. And how we can define the boundary, this is our principle. Based on the existing literature, we can divide it into the 3 areas. The upstream region, the core region, and the downstream region. And secondly, we'll try to reduce as much as possible the upstream lines, so that we'll try to maintain the same inlet velocity. So in the core region, we'll try to have the thicker grids so that we'll reduce the number of the grids. We can save the time. And thirdly, we'll try to lower the turbulent kinetic energy at the inlet. Actually, they will try to recommend the polished 2 equation models of the standard commercial software. That is a K and E equation by the UDS. Actually, it's not quite realistic. And it is quite time-consuming, so it's not quite realistic. So we'd better use the polished equation for our calculation. And then let's talk about the tree model. In our case, this is also one of our research results. As for the tree models, internationally, they have a lot of different methods to treat it. And they have different items added in it. They have the coefficient in it.
This is also referring to a study result from Japan, and we are going to use some experiment data to verify on the figure data, and that the verification shows that the result is reliable. And we've done some simple tests. We can see that with the trees, the overall field will be impacted, and when the airflow goes through the tree, the velocity reduce will be very obvious, and also this K has a bigger influence because of the tree interaction. The influence will be big. So this is the basic theory. Since we already have the calculation models, now we still need a standard to evaluate. This is outdoor data evaluation standard, very classic standard, and this is our table that we concluded. So 1.5 meter high and a 5 meter an outdoor situation which can reach the human being comfort level. Here I would like to introduce you a case study. Our colleagues of SOS is also introducing such cases. This is the location of our project, which is located in Tianjin City. This is the Haihe River, and this is the project location. In 2009, in the APEC meeting, this is the low carbon model city. Therefore, it has model significance, and we've done some study on it. This photo was provided by SNM, and you can see the overall area has a high rise and a super high rise, and this one is above 600 meters. And apart from this super high rise, there are also some green areas over there. A lot of the buildings over there are being constructed already. This is the plan for our master planning. The green areas is the green. And you can see this green area includes lawn and some low-level plants, and also some trees, etc. They all have some influence to the airflow. The first case is if we suppose there is no green area, what is the situation? And the second case is according to our current plan with the green area, what is the situation? And last case, and in some areas we will add some trees, and then what will be the situation for the airflow? So first, let's look at the computing domain. This is the area we have selected for calculation. This is our computing domain. These are some of the details we've already made in the plan. This is our overall grid. This is local grid. In order to enhance the people's comfort level and calculate accurately, we've drawn 3 to 4 grids. And these are the 3 different cases, and airflow changes in this vector graph. You don't see big differences. Let's look at this cloud graph. This is the second case. In this cloud graph, you can see that in this graph there are big differences in the speed or velocity. The color is darker, and here the dark color is lighter. So you can see there are some differences with or without the green, especially on the 2 banks of the river. When you're adding the tree, the airflow obviously reduced. There you can see that tree planting and green area adding has a very obvious influence. And because of PPT reasons, I did not clarify the figures very clearly here. They have a very big difference actually in these 3 testing points. And lastly, I want to give you a conclusion. We have compared the cases, and we found that greening design strategy can improve air distribution and decrease eddy region. And green planting planning can enlarge the uncomfortable area, especially in summertime. And also, it is difficult for the pollution dispersing around the buildings for the reason of the low velocity. We found that the case 3 is the best solution for outdoor air distribution for the reason of changing green planting area. And also, it is recommended that low vegetation, grass, trees should be planted in prevailing wind direction and densely built up areas. This greening strategy will be good for air distribution as well as pollution dilution. And right now, we are also doing some studies on the heat island. And this kind of work is already started. We also consider the heat convey issues. And when we add this influence, the requirement will be higher. Right now, we don't have a good verification method. We've done a lot of on-site experiment and model simulation to study heat island effect. We already have the plan. We want to change the architecture type or shape to optimize the outdoor environment. But now we use a simple method such as adding more green areas to optimize the outdoor environment. Thank you for your attention.